Okay, that's negative thinking. I thought overall the class did pretty dang good on, especially for a first analytical test. Usually that should be really tough, but overall I thought most everybody did pretty good. So, chemical equilibrium. Actually, we've got a couple situations here for equilibrium and non-equilibrium. But why are these not the best depictions for chemical equilibrium systems, whether you're at equilibrium or non-equilibrium? Yeah, why would they not be good depictions of that? Equation. Something's about to happen.
In equilibrium, you've got it going in both directions all the chapters.
Yeah, it's something that we're too lazy to do, especially me. When you draw a reaction, you end up doing that. You're not supposed to do just that. Both directions, right? This stuff, the reactants are reacting at the same rate the products are forming. And the products are going back to reactants at the same rate the reactants are going forward, right? The rates are the same. So it's dynamic. These examples aren't dynamic, right? So that's what I was trying to point out there. Okay. And equilibrium constants. We've got a reaction, and the small case letters are the stoichiometric coefficients. Remember that term, Marlena? Stoichiometric coefficients, right? Marlena, how would you write the equilibrium constant expression? What is our equilibrium constant? What's the symbol do we use for that? Big K, right? And that was always what over what, Christina? Okay. Raised to their stoichiometric coefficients, right? So products over reactants. C raised to little c. B raised to little b. A raised to little a, right? Okay. Units for equilibrium constants. Brad, do they have units? No. It seems like they would, though. Right? Because here they wouldn't all cancel in this one. But he's technically right. But we haven't covered why he's right yet. Right? But when you look at this, I don't see all the units canceling, do you? You only have, there's no way. I mean, if, yeah, and that's if the coefficient, who depends what the coefficients are. But he's technically right. The answer is no. But the reason why, I don't know. I guess I can tell you why. Does anybody know why? Starts with an A. Activity. We're not there yet. But man, if you're going to dose me with some drug, I don't want you to be using concentrations. I want you to be using activities. Otherwise, don't even think about it, right? So real life stuff is activities, and we'll get to that at some point. But anyway, don't worry about that for now. What, if anything, is always left out of an equilibrium constant expression? So this is an equilibrium constant expression. This is the chemical equation. What do you leave out of an equilibrium constant expression, Alyssa? Liquids, solids, and liquids. How do you know if you have a solid or liquid, Andrew, in a chemical equation? Yeah. Like if it's a solid, it'll have a little subscript S. If it's a liquid, it'll have a little subscript O. Not AQ. L. Okay. Little subscript L for liquids. What is AQ? What does aqueous mean? Dissolved in water. Or technically it means it's hydrated. That water is actually the cause for it to be dissolved. It's, you know, water. Remember, water's a polar molecule. Little O negative, H positive. They're going to orient themselves. So yeah, they orient themselves and they hydrate, especially ions. What is the standard state of a gas? Oh, hey, let's back up. Does AQ show up? You have a little subscript AQ. Something's here, subscript AQ. Does that show up in an equilibrium constant expression? Yeah. It's just what Alyssa said. Leave out these guys, solids and liquids. The standard state of a gas. What is that? Jose, what's that? Standard state of a gas. Starts with a B. Then an A. Bar. Yeah, what the heck is a bar, right? But that's what it is. 1 bar. Okay. There's a lot of units for gas pressure. There's atmospheres. There's pascals. That's what they like to use in the metric system, right? There's pounds per square inch. Okay, what is the standard state of a solute? What's a solute? Give me an example, Jenny, of a solute. Jenny, what would be an example of a solute? Solute. A solute is anything that you're going to have the little what subscript on? AQ, especially if you're dissolving it in water. Right? So name anything that dissolves in water, that's a solute. What would be its standard state? Well, it's not a gas, though. Big M, but how many big M's? 1. 1 molar. 1 molar is its standard state. Okay. And really, this standard state stuff really only comes into play when you start messing with chem or something like that, but I don't think we're going to really need it too much. Manipulations with the equilibrium constant. If a reaction is flipped, Daisy, what will be the equilibrium constant for the flipped reaction? Right? Here's a reaction, and we flip it. Reactants become products, products become reactants. How would that affect the equilibrium constant? Anybody help her? Now just flip it too. And it'd flip it, right? Because now C is now reactants, A and B are now products. Right, the equilibrium constant, products over reactants, it's just flipped. Just flipped, 1 over K. You have to flip it to get the new equilibrium constant. What if we take 3 reactions, right? Add them all up, get the new reaction, right? So you can write this guy's equilibrium constant expression, right? This guy's equilibrium constant expression, right? This guy's equilibrium constant expression. How would you get this guy's, the final answer? Yeah, it's going to be some mathematical relation, but we're not going to add them. We're going to multiply them. You pretty much have to, I don't want to spend that time to work it all out. I think the book might have, but you just multiply them, right? The new equilibrium constant would be K1 times K2 times K3.
You divide by when you subtract.
Okay. I think subtracting is going to be complicated because your stuff is going to now be missing, right? So that's a good question, right? I'm not so sure, because if you cancel things out, things could really change on you. Must not be worried about it because the book isn't, so I'm not. But it's a good question. Equilibrium and thermodynamics. For a reaction, thermodynamics is big on the spontaneity thing, Victoria. If a reaction is spontaneous, what does that mean in the world of thermodynamics? It could be, but have you had those? They're in some first aid kits. There's this plastic or this bag, and you smash it, and it gets cold. And that happens all on its own, right? So it doesn't have to be. It naturally happens. Does it mean it's going to be? When I say spontaneous, I mean. But is that what this means? No, is anyone here married? No one in here is married, are they? Well, everyone's seen a diamond ring, right?
Sure.
You wait. You'd have to Google this. It's on the order of 1 million years or so. It'll turn into a little hunk of coal. That's a spontaneous process according to thermodynamics. It's gonna happen, and you can't stop it from happening. They don't care about time. Thermodynamics has nothing to do with time. It just means it's gonna happen. You can speed it along by heating it up, and it takes a propane torch, and that takes about 90 seconds for a diamond ring. It'll turn into a little hunk of coal. But okay, so that's kind of what spontaneous means. Reaction spontaneity depends on 3 factors. There's a hint there. What do you think those 3 factors are, Albert? What influences spontaneity? I guess maybe before we should answer that, maybe we should answer this one. It's kind of hard, I think, to answer the hint and understand it's a hint unless we can answer this question. How would you answer this one? Delta G is less than 0. Delta G is negative for spontaneous processes. That was the big power with using Gibbs free energy, changing Gibbs free energy. So knowing that, now I think we can probably do the hint, Sochi. Reaction spontaneity depends on 3 factors. What are those 3 factors? Right? And here's our hint. Somebody help her? Temperature. Another one? Oh, let's back up. Temperature. Okay, temperature. Would you want the temperature to be, well, temperature, delta H, and delta S are the 3. Let's start with, just go across here, delta H. Would you want delta H to be negative or positive? And then that's really going to help things along and make it spontaneous. Negative. Right? And that's what Victoria was saying. Yeah, negative. Most often. What the question was, what would help delta G be negative? Delta H should be positive or negative? Delta G should be negative. It doesn't have to be, but it would help, right? That's all I'm saying. How about temperature? Now, when they're doing this, I don't know if you remember using it, what units does temperature have to be in? It has to be in Kelvin. So is there such a thing as a negative temperature? No. So should temperature be high or low to really help spontaneity along? Really high, right? You're subtracting it. And delta S needs to be, all you have 2 choices, positive or negative for delta S. Positive. What does that mean, by the way? Entropy, yeah. But entropy is a funky thing. It's not really what you think. You just moved into the dorm. Pretty much, right? And when you moved in, there weren't any little dust bunnies under the bed, right? You give yourself 5-6 weeks. Look under there. Now there's clumps of stuff. And the clumps of stuff is getting bigger and bigger and bigger. It's not spreading out, right? Entropy isn't that. Entropy has everything to do with chem. It has everything to do with energy levels and energy states. Oh, I have many more states available to me. You can't see that stuff. That's all entropy really has to do with. So again, that's kind of beyond us, but that's okay. I just can't help but say that answer. Okay. Now, how do we get values for delta H and delta S? For me to ask this question and for you to really give the right answer, I need to add little superscript zeros on this stuff. What does the superscript 0 mean? Usually it does. Usually it means initial, but it's not. Superscript 0. Someone said it. Standard standard states. If you have everything in your reaction, the temperature, everything in these standard states, and we haven't even talked about temperature yet, but if everything is in standard states, you can look these numbers up for every single compound in the reaction. And that's how we're going to get them, right? And that's how we did get them in general chemistry. We had a big table of delta H and delta S. And we did delta H of products minus all the delta H for all the reactants. And that's how we got our delta H for the reaction. Same for delta S, products minus reactants. You have to use big tables. But that only works if you see that superscript 0, standard state. Otherwise, you can't use the table. Equilibrium constants and the Gibbs free energy. There is a relation. They are related. Mariella, according to what this equation looks like, the more spontaneous a reaction, then K is, what would you say, bigger or smaller? Those equilibrium constants. The more spontaneous a reaction, then K is, to me it's almost easier without looking at the mathematical equation. If something's going to be spontaneous, would you expect there to be a lot of product?
Yeah.
I would think so. It's going to happen. It's going to occur naturally, very naturally. You expect a lot of product. And K is, equilibrium constants are what over what? Products over reactants. So K should be big. But the question is a little more confusing. It's asking to use this equation to get there. So you know the answer is big, but how do you get there? If it's spontaneous, delta G is what? Positive or negative? Negative. There you go. A negative times a negative, positive. So K's are huge for spontaneous reactions. The more spontaneous a reaction is, then delta G is, everybody, more negative. Yeah. Man, I do not know how to pronounce this guy's name. No one knows French, right? Nobody knows French. So no one can laugh at me when I say Le Chatelier or whatever. I don't know how to pronounce his name. So what is that principle? Jessica, what is that principle? Ooh, she's reading it from the book. Good. Read it out loud. Okay, so there's some change. First, you got to start out at equilibrium. There's some change. The system has to respond to get back to equilibrium. That's all it is. Okay? So what we're going to do is we're going to play with that a little bit. Here's a nice big long reaction, and we even have the enthalpy of the reaction. By the way, do you remember your terminology? Is this an exothermic or an endothermic reaction, Jesus? Exactly. It's negative, so that's an exothermic reaction. So we're at equilibrium. That means, again, see how we're already getting lazy in the book too? All right, we should always have double arrows. But anyway, we're at equilibrium. Will more or less of this bromate exist at equilibrium for each case? Okay, we're going to add sodium bromide solid to the mixture. Now, another thing that folks get lazy on in the book, and me too, is whenever you see an ion, what is it understood? We never wrote it, but we should have every single time. We should have wrote what on every single ion that you see? Little AQ. You can't have an ion that's not dissolved, right? So all these ions should say AQ, right? So on every ion should be AQ. On the water, you see water. So the only two choices for it is an L or a G, right? So we should probably put these little subscripts in there. I don't know if it really helps or not, but technically we should have them in there. Okay, so the question is, will we have more or less bromate if we add sodium bromide solid to the mixture? Eustacio, let's see if you remember how to play this game. Where is the bromate? Oh, there it is. The bromate is way over there on the reactant side. Here's our bromate. Number 1. Okay. Anyone remember playing this game? You have to find something. So is the sodium bromide in the reaction, or does it influence it in any way?
It's a solid.
It's a solid, but this is the one solubility rule that you really got to know for this class, and it's going to kill you if you don't remember it. There's only one solubility rule. For things that dissolve in water, whenever you had these ions, it always dissolved 100% in water. What were those ions? Group 1. Group 1 ions dissolve anything in water. That you just got to burn in your head in this class. It's going to bite you if you don't. Okay. So when I say when sodium bromide solid is added to the mixture, are you really adding a solid? No, you're adding sodium ions and bromide anions. So you look for those guys up there. Do you see it? There it is. So now you have too much bromide. However, the reaction doesn't know that. The reaction just knows you have too much product. You're going to shift to reactants. Okay, so do you have more or less bromate?
Which bromate or BRO3? Is the question.
They want to know more or less bromate, BRO3 negative. You're going to have more bromate. Right? Does that make sense? We have too much product. Too much bromide.
Is BRO3 negative bromate?
That should have it has a negative sign on it.
No, but what is bromate like a polyatomic?
Yeah, BRO3 negative. It's right there.
I just didn't recognize it.
Okay.
I was thinking it was like
Bromide is Br negative 1. Okay. That makes sense for number 1? Number 2, answer each one of these, and I'll ask you. Put down more or less bromate for each one of these. And there's no trick questions. Every single one of those is going to influence that equilibrium. There could be trick questions, but this one doesn't have any. Will there be more or less bromate for each one of these? Okay, let's see. Did you get an answer for all of these? Caroline, do you have an answer for some of these?
I think 2 is going to be more.
She says 2 she thinks will be more. Does everybody agree? So preferentially precipitates this stuff. Okay, I don't see any phosphate anywhere, but where's the interaction? Where's the commonality? Chromium 3. Good.
So it takes it out of the reactions.
Okay. Did you hear Eric? It precipitates chromium 3. So does it take it out of the reaction or bring it in? Takes it out. Okay. So now do you have too much or too little? Is it on the reactant or product side? It's on the reactant side. So do you have too much or too little reactant? Too little. You just removed it. So Le Chatelier says you got to shift towards the reactants to fill in that. You don't have enough reactant. And the reason why I say do you have enough reactant or product is it's that darn K. You said it was products over reactants. And it equals some number. We don't care even what that number is. We just know that it's constant. At equilibrium, and only at equilibrium do you get that number. So if you say there's not enough reactant, it's got to shift and get that number bigger. Right? So it's got to shift to the reactants and so we can get back to getting reactant number bigger, this number smaller, so you can get back to the equilibrium constant number. That's all the game we're playing without even doing the math. Okay. So if it shifts back there, then we're going to have more or less of the bromate. If it shifts towards reactants, we'll have more bromate. Okay. We're adding some sodium hydroxide. Where is that going to interact, Zach? Where's that going to interact?
It's going to take out some of those H pluses.
There it goes. It's going to remove this. Remove. So now with products, too little or too much? Too little. It's going to have to shift from reactants to products. What happens to the bromate? It's going to go down less. One more. 0.05 milliliters of 1.25 molar. What's the name of that? What type of acid? It's vinegar. Acetic acid. Okay. Is it one of the strong acids? No. It's not good. You're ahead of me if you're ahead of the class if you know that. But recognize it's an acid because it's got a little H hanging out there. Okay. Not a strong acid. But it is an acid. So it will provide some what? That's a commonality. Protons, H pluses. It will provide some. It will. So now on the product side, we're going to have too much. Right? You have too much product. Has to shift towards reactants. So the bromate will go up. Okay. This is really an important principle because, man, one of these guys is really expensive. That's almost how it always happens. And you use Le Chatelier's principle so that you can really optimize that all the conditions to save the most money or make the most money, either way. Okay. Here's another one that I added. I don't think you have this in your notes. If the below mixture is at equilibrium, well, more or less ammonia exists at equilibrium in each case. Okay, first one, we're heating it. Matt, we played this game in general chemistry, but I don't know if you remember it. We heated it. Now, where is heat in the reaction, though? Do you even see heat?
So, what was the question? Where's the heat? It's on the reactant side.
Is it on the reactant side?
Wouldn't we just go to the other?
Well, it's Jesus gave us a hint. He said delta H is, a while back, he said delta H is negative. But then he called it exothermic because heat is released. So that means heat has to be on which side? Product side. So I physically, when I do this stuff, although to keep myself from screwing up, it's a product. Heat is a product. It sounds odd, but it's a product. If I'm heating it, now I have too much or too little product. Too much. It's got to shift towards the reactants. The effect on ammonia is to go down. I'll have less. Okay. Whoa, less. Should say less. An inert gas is added. Now this one's tricky. See if you remember how to do this one. Monica remembers though. An inert gas is added. Now what's inert? Yeah, it doesn't. Argon. Whatever. It's not going to react with anything. All you're doing is just doing what to the system? Increasing its, there's the P. Yeah, overall mass, but pressure. That's all. I mean, you could be, if you want to increase the pressure, you can add an inert gas, which is the cheapest way of doing it. Otherwise, you got to take the whole container and smash it down or something. But that's how they usually do this. So if you increase the pressure, what's the effect on the ammonia? What was the trick to doing this?
Stoichiometric coefficients.
Add up the stoichiometric coefficients. Eric says he's right. Whoop. So on, remember playing this game? On this side, I have how many gas molecules? Everybody see 4? On this side, I have how many gas molecules? 2. And all you're counting up is the gas molecules. Does a liquid or a solid laying in the container isn't going to help you exert any gas. It has no effect on pressure. It's the gas molecules that create pressure. So that's all we're interested in. So which side, again, the pressure can't tell the difference between molecules. All it knows is you have high pressure and low pressure. That's all it can tell. Which side is the high pressure side? The reactants or the products? Why is it the reactants? You're right. Because you have more gas molecules. That's the only reason why. You have a lot of gas molecules. That's the high pressure side. High pressure side. That means this has to be the low or lower pressure side. Okay. It's at equilibrium. You have your nice equilibrium constant, whatever it is, right? The nice dynamic equilibrium is going on. The amounts of products and reactants aren't changing, and they work out, so you just get that equilibrium constant number. Everything's perfect. You increase the pressure. You increase the pressure. That's the same effect as what? Too much reactant or too much product? It's too much reactant. The system can't distinguish between gas molecules, but you increase the pressure. That's like pretending you're on the high pressure side. Right? You have to get rid of that change. You have to go back to the equilibrium constant expression. Products over reactants, get that number back. So if you're on the inert gases added, it's just like dumping in nitrogen gas or hydrogen gas. Either one would work. So that means you have to get rid of that excess pressure, go to the low by going to the low pressure side, and that's going to ammonia. So that would be one good way to help enhance, well, I should say more ammonia. Oh, I can't even write. Okay. Reaction quotient. Do you remember that? What was reaction quotient? What was the symbol for it? Does anyone remember? Q. Big Q. Good. And it was always what over what? Products over reactants. It's just like in the equilibrium constant expression. Well, if it's just like products over reactants, if it's the exact same expression as an equilibrium constant, why don't we use big K then? Well, they're all concentrations. Yeah, so Q is concentrations of the products over the concentrations of all the reactants, raised to their stoichiometric coefficients. Well, you're not sure if it is. That's the whole point. You're not sure if it is. You're given all these concentrations. You don't know if you're at equilibrium or not. It's kind of silly. I mean, you plug it. To me, all you need is that one expression, K, and if you plug it in and you do not get the K number, whatever that book or Google says, you know you're not at equilibrium. But I guess it's kind of confusing, because if you are using K, then you should be at equilibrium. So I can see the argument for using Q, right? You're given, like in this question, they just throw a whole bunch of reactions at you. Sorry, a whole bunch of concentrations at you, right? Are you at equilibrium or not? Well, they have to tell you what K is, because if they don't, there's no way you could tell. You plug in all the concentrations of the products raised to their stoichiometric powers, divided by the concentration of the reactants, raised to all the stoichiometric powers. If and only if you get what, will you be at equilibrium? 2 times 10 to the 11th, right? Okay. So You can probably work that one out at home, right? You agree?
But how do you know which ones are products?
Oh, it's from the reaction came way from where? Came way over here, right? We probably should do that one, right? Let's do that one. We have time. Since we're working out problems anyway, see if you're at equilibrium or not, right? Go scroll back up and see you have the equilibrium, you have the reaction. Write the equilibrium constant expression and plug everything in. I'll add one here to see if I can confuse you. The concentration of water is 55.4 molar. That is the concentration of water. But are you going to use it? Better not. Exactly. I forget what the heck the reaction even was. Bromide, dichromate, 8 hydrogen ions. What is that? Oh, wait. All right. Let's see. Bromide is. Where is it? Well, there's no way you can get 10 to the 11th out of this, right? But we can at least predict which direction it's going to shift. We can do that. 1.01. 9 to the 8th. Chromium squared. Did anybody get an answer for this?
166.1.
166 about?
So if it's less.
Yeah, that'd be the better question, right? So if you get 166, hopefully, you left H2O liquid out, and if it's less, that means what? It's going to shift where? Right? You're not at equilibrium. Which direction is it going to shift? Well, I hear both. I hear products and I hear reactants. I think it's easier to think of just, because K is always what over what? Products over reactants. Always think in terms of products. Life is so much easier because it's up on top. So Q is 166. Oh, look at that. I wrote a K, didn't I? Doofus. Okay, Q is 166. So do I have enough product or too much? Do I have too little or too? I have too little product. So it has to shift towards products. So I just think in terms of products all the time. So shift to products. It's a lot easier than to memorizing anything. Okay. Let's write some. So go ahead and write the equilibrium constant expression for A and B there. Make note of px. Yeah, you have to add it. You add the B. There's no B in your book. I just added that before class started. So Andrew, how'd you do A? Ag is silver. Yeah. Good. Phosphate, good. Raised to the, yeah, well, the 1 technically. Yeah. Okay. How about B? Oh, let's go back to, who haven't I picked on? Shelby, I haven't picked on Shelby. What did you do for B? Yeah, but how do you write NH3? They want you to use, do you see it? Whenever you have a gas, they want P probably stands for pressure, right? So P with a subscript NH3 raised to the what power? Second. For every gas has to be capital P. Mm-hmm. Yeah. Yeah, exactly. Okay. So this is the thermodynamic equilibrium constant expression. When just to let you know, when you see equilibrium constants with a little c down there, then they do not want you to use p's. They want you to have everything in terms of concentrations, molarities. Okay, so that's coming up later, but just to let you know it is coming. C stands for concentration. Concentration. Yeah, so the pressures need to be in what units? Bars. Yeah.
Okay, C would be molarity.
C, everything's in molarity. Even the gases are in molarity. But we're not here yet, so I don't want to confuse you. I just want you to say that there will be a time when we use brackets for everything. Except what two things? Solids and liquids. Good. All right. Well, it'd just say stuff like the pressure of ammonia is like 2 bars, and the pressure, you just cube and square the number. Yeah. Okay, I want to hand out the exams. There's some more here, but we never finish everything anyway. Okay.
Is there any way, like, in case we don't finish anything, like, if you could post them online or something with just the correct answers, so that if we do both the answer, we could just check with you?
You can come by.